My name is Sander Mak, and this morning we'll be talking about modular Java, and especially about the module system that has been introduced in Java 9. So quick poll, who has already used Java 9 or 10 by now? Okay, I see a few hands, but not too many. Well, that's a good thing because you will learn something new, you'll see something new. On the other hand, it might be a bad thing because, well, you're already quite behind if you're not at Java 10 already, and we get Java 11 in September, and that's a whole different story, but still great that you're here, and I hope we can show you something new and something that you haven't seen before. So, as I said, my name is Sander. I work with Luminous, which is a software technology company in the Netherlands, and we do both consultancy and product development. And maybe if you've done both as well, then you know that this is a different kind of game that you're playing in terms of software development. If you're doing consultancy, small projects, then, well, you start with a team and you build something and then you're on to the next thing. If you build products that you maintain for 5 years, 10 years, maybe even longer, then you start thinking about maintainability, extensibility a lot harder. And that's where we believe that modular development is very, very important. So we already had a very modular approach to software development, mostly using, for example, OSGI, which was sort of the de facto module system before modules came along in Java 9. And then Java 9 came along and we actually get a module system in Java itself. So me and a co-worker started to quite deep dive into Java 9 and to the module system. And we actually dove so deep into the early access releases, etc., that O'Reilly asked us to write a book about this. And what you hear today and what you'll see today is sort of a summary of what we learned and what we saw with modules in Java 9. So this morning I would like to talk first a little bit about, okay, so why is this modularity thing so important? At least important to us, and I believe it's important to everyone who wants to create maintainable software. After we looked at that, we're going to look at Java itself and what it offers in terms of the module system and support for modules. And while doing so, we will also encounter that just having modules doesn't mean that you have an extensible or modular application. You also need to think about the design of your code. And in addition to modules, you can also use services in the JDK in Java. And we'll see how these interact with modules and how they can make your code more decoupled and more extensible. Last, we'll look at a new feature that's completely enabled by modules in Java, and that's called linking. And linking allows you to create a so-called custom runtime image for your application. And we'll see what it is, but I think it's a very cool application of using modules in Java. Now let's get started with modularity itself first. And for us, what we like to say is that modularity is the ultimate agile tool. So agile is all about designing for change, right? So how do you design for change? Well, if you think about it, we have these nice pictures on the whiteboard, right? When we design systems, we have these blocks of functionality that are coherent, that belong together, and that we think are good design. But somehow, things often get lost into the translation when actually implementing these designs. And what modularity actually does is it allows you to take these nice boxes that you draw on the whiteboard and also put it into practice, put it into your code. And we'll see that you can do that using the Java module system, but you could already do that using other module systems as well in Java, and even in other languages. I mean, JavaScript even got modules, and then in other languages as well. So this is not something that is a feature of Java itself. This is a architectural concept that's bigger than just a language feature. And if you have a modular architecture that in turn translates into a modular code base, this will allow you to iterate quicker, because you will have more a view of what the impact of changes will be. You can contain changes inside of modules if you encapsulate stuff. We'll talk about that later as well. And you will have a complete view of all the explicit parts that are in your code base and how they relate together. Because there are actually two important principles when you think about modularity. And the first one has to do with hiding stuff. And that sounds a bit counterintuitive maybe, because we're all about openness, right? Open source, etc. So why would you want to hide stuff? And it has everything to do with the fact that anything that you don't hide is actually something that you can consider API, a public API that other people use and that other people depend on. And If you just have a piece, a component in your system, and other people start using that component, and they start to depend on these nitty-gritty implementation details, then you can't really change these implementation details without breaking the consumers of this component, without breaking the external users of this component. And that's bad, of course, because you do want to be able to change your implementation details. And, well, we know this better as encapsulation or implementation hiding. And this principle isn't new by any means. We already apply it at the class and the object level, right? We have private fields, we have protected, and we have all these matters in Java already at the low level of objects and classes. What modularity does and what the module system does, it takes this to a higher level where you can actually group packages together and designate them in terms of being encapsulated or public API. So, of course, you want to minimize your public API because your public API is something that you need to support, that you need to evolve, that you need to be aware of that other people are talking against this API, and, if possible, encapsulate as much as possible inside of these module boundaries. Now, I said there were two principles, so encapsulation is one principle that's very important when you talk about modularity. The other one is that if you start creating these modules, you'll end up with lots of pieces. And the question is, how do these pieces fit together back into a single application again? For that, you need to know what module needs another module, and so on and so on. So explicit dependencies between modules is another very important concept that you'll see in every module system, also in the Java module system. And as you can see here, these explicit dependencies between modules hopefully are mediated over service contracts. Like in Java, we have interfaces, which is the most natural point of interaction between different components, but it could be anything really. The point here is that A, you want to be explicit about what is encapsulated inside of a module boundary and what is public, what is exported outside of a module. And B, you want to have these explicit dependencies somewhere encoded into your modules because you don't want to keep track of this yourself by hand. Now, in Java, like I said, with Java 9, we got a module system. And it was also known as Project Jigsaw. You may have heard of that. The spec itself is the JSR 376. If you want all the details, I recommend you read that, but it's pretty dry. So we'll get the summary in this talk. The question is, why did this actually happen? What were the goals of adding this module system to Java? Actually, when you look into this, it's a rather selfish goal that the JDK team had for why they wanted to have a module system. Because what you saw in the JDK itself is that it became the ultimate monolith. There was a single rt.jar, runtime jar file, containing the whole Java platform. There were like tens of thousands of classes in there. And what happened in this code base is what happens in any code base that's 20 years old. You get these very, very strange dependencies between different parts of code, for example. So you change something here, and something breaks there. I mean, we've all experienced that. And this makes it harder to evolve such an old and big code base. The other thing that happened has everything to do with the encapsulation that we talked about. So in the JDK, we have public APIs. That's the APIs that we as programmers program against. But there's also lots of implementation classes to implement the functionality. And it turned out that in the past 2 decades, lots of frameworks and even application code started using and depending on these internal implementation details of the JDK. Now, this, in theory, wouldn't have been a problem because Oracle and before that Sun could have just said, okay, you're using non-public APIs. We're free to change those, so we'll just do that, and then your library or your application breaks. Well, bad luck for you. But that's all right. I mean, you're just using stuff that you shouldn't use. They could have done that, but they didn't, because Java has always been very, very big on backward compatibility. And what happened instead is that it became harder and harder to evolve these implementations, these implementation classes that libraries and applications depended upon, because, well, yeah, they effectively became public APIs. So what was sorely needed in the JDK itself was a way to chop up this big runtime monolith into pieces, into nice modules, and also to be able to encapsulate the implementation details and to only expose the public APIs to us as developers. So that's actually the reason why it all got started. And of course, this is not something that's unique to the JDK. This is something that any code base can benefit from. So that's also why we can use the module system. And it's the same module system that has been used to modularize the JDK that we can use to modularize our applications. Now, what does the JDK look like? Well, here we have a small subset of modules that are in the JDK. And these are the modules that are defined in the Java specification. If you look closely, you'll see that they all start with the Java dot, except for two yellow ones, which are different. It's not important what the names of these modules are, but only the fact that we have this overview, that we can generate such a graph of dependencies between different functional parts of the JDK, is already really, really great. And in the JDK, we currently have more than 90 platform modules, so modules that modularize the platform itself. So like I said before, we had this big monolithic runtime jar. Now we have these small pieces, and these small pieces all have explicit dependencies, so you can see how they fit together. For example, there's a Java SQL module in there, and it has two arrows going down to Java logging, which, well, sounds fair enough, right? Because it might do some logging and during database access. But it also has a dependency to the Java XML module. And that seems a bit weird, right? And just the fact that we can see this from a picture and that we can ask the question, okay, so why is there a dependency from Java SQL to Java XML? That's a big win already. And to answer the question, it's because way back when people thought it would be good to have XML columns in databases, and people thought it would be nice to add this to the SQL and the JDBC standards. And well, that's how the dependency from Java SQL to Java XML can be explained. So there's a reason for it. Might not be a good reason, but anyway, that's it. But we can learn this by looking at a module graph, which is good. Now at the bottom we have a single module called Java Base. And this Java Base module contains all the foundational classes of the Java platform. So it contains like the string class, Java lang object, the collections, everything that no other piece of code can do without. So we'll also see that every module that's in the JDK and every module that we can create as developers will always have the implicit dependency on Java Base. You don't have to do anything for that to be the case. It's a bit like like that we also have a implicit import of the Java lang package in every source file. Even though you don't really think about it, this is what happens. And the same goes for this dependency on Java Base. Another thing, if you keep staring at this picture, is that you might find that there are no cycles in this module graph. And this is no accident. This is by design. So we can have cyclic dependencies in Java between classes. We can have cyclic dependencies in Java between packages. And even though we can, it's not sure whether it's a good idea to do so, to have these cyclic dependencies. But at the module level, you cannot have cyclic dependencies. And again, if you have cycles in your code, there might be a good reason for that, but mostly cyclic dependencies between different parts point to design errors, point to things that should be handled differently if possible. And at the module level, well, if you have two modules that have a cyclic dependency, they're effectively almost the same module because they need to be built at the same time. And if they have such a tight relationship, then you should ask the question, why are they two separate modules? So modules always have to be acyclic. Now this little fella, the class path, I think we've all encountered it, right? And we've all fought with it, and we've all tuned it and tried to make it work, because you can easily miss a jar file, or you can easily have multiple versions of a jar file on the class path. And this leads to runtime exceptions, of course, and always at the worst possible moment. And it's just something that doesn't work very well, even though we have some tooling to help us nowadays with all the build tools and all the other stuff to get the class path right. Still, it's a very brittle mechanism. So what modules can offer us is a way forward, a way to say goodbye to the class path. That doesn't mean that as of Java 9 there will be no class path anymore. To the contrary, it's still there and it will be there for a long time, I think. But we also have an alternative now using modules instead of just plain jar files. So what is a module? A module is a piece of Java code that groups together some packages that belong together, that have a functional purpose together. We give it a name, for example, my module, like here. And if this module needs another module to do its work, it needs to be explicit about this dependency. And we call this a requires relation between modules. So we see that here my module requires a module called other module. And if you have a dependency on another module, like here we have my module which has a dependency on Java base, and we already knew that every module has a dependency on Java base, that doesn't mean that you can use all the code that's inside of Java base because, well, we talked about encapsulation already. That's in play here as well. So on the top we see that there are some public packages like Java lang, Java time, Java util. These are the exported packages of this module, of the Java base module, and these are the packages that we can use in our my module code. But there are also encapsulated packages, com.sun and JDK internal, and these are all the packages that I talked about previously that were being abused by libraries and by applications before the module system. Now, in the module system, if you have these packages encapsulated inside of a module, it cannot be used by other modules from the outside. And you might be thinking, okay, well, but yeah, we have reflection in Java, right? And with reflection, we can work around everything. Well, that was true, but not any longer. Even reflection cannot break through this strong encapsulation of modules. So this is a really powerful way to shield code from being abused by the outside world. So these access checks really do happen at a very, very deep level in the virtual machine. So some people that listen to this and say, okay, well, that sounds very good. There's now a module system in Java, but then we already have this OSGI thing, which sort of solves the same problem. So why didn't they just use that? Now, aside from the politics between Oracle and the OSGI alliance, which isn't very good, there's also some technical reasons why this was very hard to pull off, because OSGI is more a runtime module system based on class loaders, based on concepts that are already in the JDK, whereas the module system in Java is also something that's applied at compile time, that's applied at runtime, and it would be very hard to retrofit OSGI in such a way that it would achieve the same goals. And in that sense, it would be very hard to use OSGI to modularize the JDK itself. It's not impossible, just very hard, and it would require changes to OSGI itself as well. So then the question becomes, okay, so they chopped up the JDK using their own module system, so why wouldn't we just keep on using OSGI if we have an OSGI-based application? And that's actually a very fair point, and you can still do that even in Java 9 and 10 and later. There's no reason why you can't use OSGI anymore, because it will just run on the class path, it will run the same way as before, and you can keep using OSGI. One of the reasons that you might consider at least for new applications, not using OSGI, but using the Java module system, is because the Java module system is now actually part of the official language of the platform. So we already see that tooling has embraced this. So IntelliJ, Eclipse, Maven, Gradle, they all know how to handle Java modules. And up until now, in the past 10 years, the tooling around, for example, OSGI and Eclipse and IntelliJ, it just wasn't a very good story. And you see that in the short amount of time that Java 9 and Java 10 have been out, much more has happened than in the decade before with OSGI. And tooling is very important. We all know that as developers. So enough talking. I mean, we talked a bit about why you would want to have a modular code base. We looked at the basics of how it works in Java. So it's time to look at some code, right? So for that, I'm going to show you a demo application, which is also the demo application that we use throughout the book to illustrate all the concepts. And it's called EasyText. And EasyText is an application that can read in some text file and will calculate a complexity metric on this text, and it will print it out back to the console. And for this application, we're going to use two modules. There's a CLI module for the command line interface, which is responsible for reading in the file and chopping it up into sentences. And then there's an analysis module. And this analysis module is responsible for performing the actual textual analysis. And of course, there's a relation between these two because they need each other. Now, let's go to the code. So what I'm showing here is a very simple project containing just a source folder. And this source folder doesn't contain my package hierarchy directly. Instead, it has two module directories. And these module directories map to the modules that we saw on the slide. So there we have an EasyText CLI module directory. And what is a module directory? Well, it's a directory containing code. So here we have just a simple package hierarchy and a main class. And it also contains a so-called module descriptor in module.info.java. So if you look at this module descriptor, it's fairly simple, right? We have a module keyword followed by the name of the module and a body of the descriptor, which is currently empty. And if we look at the other module, the EasyText analysis module, we have the same pattern. There's another class, /Kincaid. /Kincaid is a type of text analysis algorithm. And there's also a module info, and it contains the module keyword and the name of the module. Now you might be wondering, okay, so we get new keywords in Java 9 and 10 and later. True. So how will this affect existing code that may, for example, use variables with the name module or something like that? And fortunately, they've thought of that. And module and all the other keywords inside of this module info Java file are only keywords in the context of module info.java. So you can still use module as a variable name and so on. So that holds for all the keywords that we'll see in this module descriptor. So just a quick peek at the code. We have a public class, main, and there's a main method. And we're trying to read something from the file system. And then after we've done so, we chop it up into sentences. And then we instantiate this /Kincaid class that's in the other module. And we call analyze on it. And we pass in the sentences. And we print the result. So how do we compile this with modules? For that, I'm going to use the compiler directly. And instead of the normal source path, I'm going to use the module source path like this. And it knows how to handle the layout of a single source directory with multiple modules in there. We need to provide an output directory. So we get the compiled classes into the out directory. And then something that people often forget, because we typically use Maven or Gradle or whatever build tool that does this for us. But if you want to compile Java files, you need to provide them all to the compiler. And in this case, I'm going to use a little trick to just find all 4 Java files and pass it to the compiler. So this will pass both the module info files and the main and the /Kincaid class. So we have everything in place. And if we try to compile this now, we actually get an error, which is kind of strange, right? Because everything is right there that we need. But it says, okay, package Java Modularity EasyText Analysis is declared in module EasyText Analysis. Okay, so far so good. But module EasyText CLI does not read it. And does not read it means it doesn't have a requires dependency to this other module, which is fair enough because, well, our module descriptor is empty. And if we work with modules, we need to be explicit about our dependency. So here, if we want to use code from the EasyText Analysis module, we need to tell it that this is okay to the module system. So we're going to do it like this. We have requires EasyText Analysis, and we're going to try the same compilation again. And again, we get an error, and it looks very similar, but it's different. Now it says, okay, this package, this analysis package, is declared in EasyText Analysis, but it does not export it. So that's the other side of the coin, right? We do have an explicit dependency now, but because we don't say anything in our analysis module descriptor, by default, every package is encapsulated. So only if you are explicitly exporting a package, and we can do that using the exports keyword, only then it will be usable for other modules. So let's do it like this, EasyText Analysis. So in this case, exports is followed by a package name, and the requires on our CLI module is followed by a module name. Now, if we compile, we actually get output. And this output reflects the same module structure. So we have the analysis module. And as you can see, the module info is also preserved at runtime. So we have this information at runtime as well about the explicit dependencies and the exported packages. And if we try to run this, we can use the module path rather than the class path. And we set it to the out directory. And rather than starting just any class, we're going to start a module. And in this case, we want to start the EasyText CLI module. And because we haven't created a jar file around it yet with an entry point class, we need to be explicit about the class that we want to start from this module. And in this case, we just want to start the main class. And it gives us a welcome text, and it says, okay, please provide a file name as your input argument. Okay, let's give it some test input. And we get back a Flashkin case score. So this is how you create a very simple application using 2 modules. And we saw that the compiler already helped us enforce module boundaries and force us to think about the dependencies between modules. And this may seem like annoying additional work, but this is actually the key of modularity. It's thinking about, is this a dependency that should be there between these 2 modules? And if yes, then it's okay to add it. And if not, then something in your design is lacking and you need to improve it. And the same for the export versus encapsulated packages. You need to be very explicit about something in terms of, is this publicly supported API or is this an internal implementation detail which I want to be able to evolve independently? Now, we used the module path to run this application, and we all are used to the class path, and this looks pretty similar, right? So you might be thinking, okay, so what's the big deal? What's the difference between this module path and class path? And the best way to illustrate this is by removing, for example, the analysis module from the module path. Now, if I start this application again, if this were the class path, then I would get some kind of class not found exception at runtime. So it starts to initialize our code, starts to run the code, and tries to load the class that it needs, and it can't find it, and it blows up at runtime. If you do this with the module path, however, you will get an exception even before the application is started or bootstrapped or whatever. And in this case, it says, okay, this module EasyText analysis, which your EasyText CLI module requires, isn't found. So please fix this first before starting the application. And this is also what's called reliable application composition in the spec of the module system. And this is something that can be done because of the explicit dependencies that are recorded in the module info files. That's something that's just not possible with plain jar files. All right, so let's get back to looking at what modular applications actually means, because we now have 2 very simple modules. And if you look at them very closely, then you might conclude, okay, but this isn't very modular or extensible, because the CLI module knows exactly which implementation class to instantiate from the analysis module. And this sounds like a very tight coupling, right? So what we would like to have instead is that these modules communicate over some kind of shared interface without knowing their implementation details. So how do we get to that point? How do we get to the point that we can actually use implementations from another module without knowing about these implementations? And like all problems in computer science, it can be solved by adding another layer of indirection. So again, this is also the solution that is chosen by the module system. And what you can do is you can use the services mechanism. And the module system, the JDK, offers a service registry where provider modules can provide implementations of a service interface, and where consumer modules can ask the registry, okay, please give me implementations of this interface, and they don't have to directly know each other. This is, of course, a form of inversion of control, also popularized by frameworks that do dependency injection, like Spring and Juice. So the concept is similar, but the techniques that are used are a bit different. How does this work in terms of modules? Now, if you want this to work, then we need some kind of shared contract between the providers and the consumers. So typically, you put those in their own API modules. Like here, we have a module myAPI, and it has a single package, com.api, containing a service type, and we export it because, well, that's what you do with a public interface. Now, on the consuming side, we have to require this API module because we need to know about the interface type that's inside of the com.api package. But rather than requiring our implementation module, we say to the module system, okay, we want to use anything of type com.api myservice. And myservice is the shared interface between consumers and providers. So there's no direct relation to any provider modules here. On the provider side of things, we have a requires my API again, because, well, we need to implement the interface in the provider. But rather than exporting our implementation class, we say in this case, we provide something of COM API my service with my provider, my service impl, where my service impl is our implementation class. And the crucial bit here is that the my provider package is not exported, right? So before we had to export our package containing the implementation class. Here we only provide it to the service registry. And the services mechanism in the JDK, in the module system, has the power to instantiate this my service impl by breaking through the encapsulation of the module. But no other module and no other piece of code can do that. Only the module system can do that. Now, the last piece of the puzzle is, of course, how do we access these implementations at runtime from the consuming side? So inside of my consumer, you can use the so-called service loader API. And service loader has been part of Java for a long time already. It's been part of Java since Java 6, I think. Only the way to use it was a bit awkward, using text files in the meta-in folder, and well, some frameworks that use it, and the JDK used it internally. It's just now much more usable with modules in Java 9 and 10 and later. So you call service loader load, you pass in the service type that you're interested in, and you get back a service loader object, and it conveniently implements the iterable interface, so we can just use a for each loop over it and just start using all the services that come back from the service registry. So in your code, you need to be aware of the fact that it can be one implementation that's returned. There can even be zero implementations or multiple. So you will have to deal with this in your code. And how you deal with this is very domain dependent. Now, how can we apply this to our example? So what if, for example, we wanted to add an additional analysis to our application? In the previous situation with the two tightly coupled modules, if we were to add another analysis module with a different implementation, then we would need to update the module descriptor of our CLI, because we would get a new require statement to the new implementation. We would need to change the code in our main class, because we need to instantiate this new implementation type from the new module that's added. And we would need to recompile, etc., etc. So that's a lot of changes for a fairly simple concept of adding a new analysis. So what we would like to do is to extend our application in a more seamless way, in a more modular way. And we can do that using services. I want to show that. The other aspect of extensibility has to do with reusability. So I want to show that we can also create another front-end module, so to say, that doesn't use the command line interface, but uses a GUI that uses the same backend code as the CLI module that we saw before. Now, before we dive into the code, a quick overview of what we'll see. So we will have an API module containing an analyzer interface, because that will be the shared contract between the consumer and the provider modules. And we still have our EasyText CLI module, the command line interface application, but we now also get a GUI module containing a JavaFX implementation of the front end. Now, our CLI module didn't have any dependencies. It only had a dependency on Java base, which is implicit, so we didn't have to mention that. But since we now use JavaFX types, we need to be explicit about this dependency from the EasyText GUI implementation to the JavaFX graphics and the JavaFX controls. All right, this will be awkward typing later, but we'll see how that goes. And so we need to be explicit about the dependency to these two platform modules as well. And the other thing that you see at the bottom of this picture is that we now have two implementations, two provider implementations, the Kincaid one that we already saw, and there's a new Coleman implementation. But the crucial bit here is there's no direct requires relation anymore between the two front-end modules and between the two implementation modules. Only at runtime, these come together using the service loader API that we saw previously. So let's see what that looks like and get back to the code. In this next example, you can see that we already have a bit more modules. And if we go into the API module, There's the analyzer interface, which is just a plain Java interface, nothing strange here. It has a getName method, an analyze method, and well, there's nothing module or services specific in this interface. Looking at an implementation or provider module, we can see that the Coleman algorithm is implemented in the Coleman Analyzer class. Again, just a plain Java class. There are no special annotations. It has a still, which one should I use now? All right. It has the getName implementation and the analyze implementation, which has the formula for the text complexity, but it's just plain Java implementing an interface. Looking at the module descriptor of this module, we can see that it requires the API module because, well, there's the analyzer interface that we're currently implementing, and it has this provides with statement, where the with contains the implementation class in the Coleman package, which again isn't exported. So even though you could get a dependency directly to this Coleman module if you wanted to, you still wouldn't be able to use this class. And it's a public class, right? So this is a big change from how it worked in Java before. A public class is now only usable from outside of a module if it's actually in an exported package. Looking at our CLI code, things are mostly the same, except for the way that we invoke the analyzers. So rather than instantiating the implementations directly, we do a service loader load call with the analyzer interface, and we loop over the analyzers and just provide the output to the console. Last, we talked about this GUI module, and again, if we look in the implementation, we see lots of JavaFX types, because it's a JavaFX GUI application, and in the main method, we also do the same service loader load call, so we'll find the same service implementations, and by doing it this way, we are decoupled from the implementation or the provider modules. And if we run this, just to show that it works as well, then you can see that we have two algorithms to choose from. So a Coleman gives a different value than the Flash Concave algorithm, which is to be expected. And if we look at our module path, then let's see. I need to do it differently because I want to show it based on jar files. All right, so if we look at the module path, we see that we have all the jar files now in here. And if I, for example, remove the Coleman provider module in this case, and let's move it to trash. And what I want to show you is that if I run the application again, and I haven't changed a single line of code, and I'm not going to recompile, I'm just going to run the same application with a different module path. Then we see that we only have the Flash Concave implementation left. And this works the other way around too. So if I would add provider modules to the module path containing analyzer implementations, these will be picked up automatically as well. So this is a very nice way to create extensible applications. All right. So there's one topic left for now, because what you see now is how to create modular applications and how to actually decouple modules using services. But there's also a next step that you can take if you create modular applications using Java. And that next step is using the tool JLink. And JLink is a tool that creates custom runtime images. And you can think of a custom runtime image as a sort of a Java runtime that's generated for you that only contains your application modules and the modules from the platform that your application actually needs to run. And these are all bundled together into a single distributable runtime image. So the idea there, of course, is that not all applications use all platform modules. So it would be wasteful to ship all platform modules with your application if you only use a simple subset. So these custom runtime images are smaller than a full Java installation plus your application running on top. Another benefit of JLink is that it's a point where we get the whole program together at link time, which allows for nice optimizations to be applied there as well. and there are a few implemented already in JLink. I think this is an area where the tool will definitely keep on growing, keep on giving more benefits and more performance optimizations. But this is really something that we didn't have before. We had compile time in Java, and we had runtime. And at runtime, of course, the just-in-time compiler gave us lots of optimizations. But there was no phase in between where everything came together and where we had the possibility to do whole program optimizations. So that has changed. And I want to show you how this works using our easy text services-based application that we just saw. So let's get back to the application again. And I'm going to show you how to use JLink on that. And for this, I just threw away a jar file, so I want to reinstate that, just to make sure that we have everything in place again. All right. And I'm going to show you how to invoke JLink, hopefully. Yeah, there we go. So we call JLink, and we have to define a module path, so we point it to the jar files of our EasyText application, but we also point it to the modules of the JDK that we want to create a runtime image for. And this might be a bit strange, because we didn't have to do this when running the application. It just implicitly took the modules of the current JDK that you're invoking. And this has to do with the fact that JLink images that are generated are platform and architecture specific. So in this case, I just pointed to my own Mac JDK, and it will create a Mac runtime image. But I could also download, for example, the Windows JDK to my Mac and point JLink to the Windows modules, and then it would just create a Windows custom runtime image. So you can cross-target using JLink as well. Now the next thing I need to do is to add the module of my application, that's sort of the root module, to JLink, where it starts the resolution process. So it starts to create a module graph of all the modules that this application needs. And it uses the requires relations between modules to do so. Now, in our application, we also had the provides and the uses statements. And by default, JLink doesn't use these relations to resolve dependencies. It could do so, but it would have some side effects of triggering lots of dependencies that are expressed in terms of provides and uses in the JDK itself as well. So in this case, I opted to be explicit, and I just instructed JLink to also include the Coleman and the Kincaid provider module. I also designate a launcher script that's generated into the custom runtime image called CLI, and it will just start the EasyText CLI module that we provided. I can strip some debug symbols, compress the image, and finally output this runtime image into the image directory. And if I do so, and I look at the image directory, there we go, it's actually just like a tiny Java runtime environment. There's a bin, conf, include, legal, and lib directory. So if we look into the bin directory, we can see that there's the Java virtual machine, so the Java command is there. There's a key tool command, which also typically is shipped with Java. And there's our CLI script that we asked to be generated. And if we just run the CLI script, it will run our application without having to configure the module path, without having to do any setup or whatever. This is all handled for us, which is kind of convenient. Now, the interesting thing is that the size of the generated image is only 23 megabytes, which, okay, admittedly for a command line application still is big, but for a Java application, a full-fledged JVM and everything that comes with it, it's actually quite small. Because if we compare this with my Java home directory containing the full JDK, you can see it's more than 500 megabytes, right? So that's a very, very big difference. Last, we can also ask our custom runtime image that has been generated which modules are actually bundled into this custom runtime image. And looking at the output, we can see, okay, the EasyText CLI, obviously, because, well, we provided that as an input. But it also saw that we had a dependency on the API module, so that was calculated automatically, and just Java base from the platform. So we only have a single tiny module of the Java platform itself currently in our runtime image. Now, if we do the same for our GUI application, and we create the image, so the only change here is that instead of the CLI module, I'm going to bundle the GUI module. We can see that has an effect on the size of the image. It's now 47 megabytes. So why is that? And that's easily explained by looking at what modules have been bundled into the custom runtime image now. Because remember, the GUI module uses JavaFX and JavaFX types. We had an explicit dependency on those. So you see that these JavaFX modules have been included, and they in turn have transitive dependencies, for example, to JavaFX base, Java XML, prefs, desktop. And I can tell you the desktop module is a pretty big one. So that's the reason why this image is bigger. And it also shows how you can scale your custom runtime image with your needs, with the needs of your application. If you have a typical web application, you probably don't have to ship the Java desktop module. So things like that really help you to create an optimized image. And you can use this to ship to your customers or to create a very small Docker image, for example. So these are all ways that you can use the JLink tool. It's an optional tool, so you don't have to use JLink, but if you do modular development using Java and you use modules, then this is a really nice benefit that you get for free if you want to use this. So with that, it's time to start wrapping up. And I hope I've shown you what you can do using the module system in Java. This is not something that you can apply overnight, right? Because modular development is something that you really need to think about all the way from your architecture to your design to your code. And if you currently have an application that's, well, sort of a big bowl of spaghetti, then this won't be easy to apply. It's not like the lambdas, for example, that we got in Java 8, which were a fairly small and localized feature. You could just take some inner class and just turn it into lambda. This is not like that. This is really about design and the architecture of your code base. But that doesn't mean that it's less important. I think it's even more important because it will help you to create more maintainable and extensible code bases. So by having modules in the language, I really like the fact that it helps to force tool vendors and to force essentially everyone who's in the ecosystem of Java to think about modules and to support modules. So that's definitely good as far as I'm concerned. And it remains to be seen, of course, what the adoption will be in practice. We really intend to use modules to their fullest extent because we do believe that modular architectures are the way forward. But still, you now have the option to do this in Java natively. So with that, I wanted to point out that if you want to learn more about this, you're welcome to go to javamodularity.com, where you can also find info about the book, which I highly recommend, of course. I do also have some content on Pluralsight. If you have an account for that, I highly recommend it as well. If you don't, I do have some free months of Pluralsight, so if you drop by, I'd be happy to give you one of those. And also, if you have any questions, please come up to me after the talk. I'll be here all day as well, and I'd be happy to chat and exchange experiences about modular Java. And with that, I'd like to thank you all for your time and your attention.